Section 2.5 Informational Divergence. Definition 2.28. The informational divergence between two probability distributions P and Q on a common alphabet X is defined as dpq equals summation x px log px divided by qx. And this can be written as expectation with respect to the distribution P log of px divided by qx. In the above definition, we take the following conventions. First, the summation is over the support of P. Namely, summation x refers to summation x in SP. Second, for any constant c bigger than 0, c log c over 0 is equal to infinity. Therefore, if dpq is less than infinity, then px bigger than 0 implies qx bigger than 0, or the support of P is a subset of the support of Q. The divergence dpq measures the quote-unquote distance between P and Q. Note that dpq is not symmetrical in P and Q, and so the divergence d is not a true metric. Also, the divergence d does not satisfy the triangular inequality. Lemma 2.29 is an extremely important inequality in information theory called the fundamental inequality. It says that for any a bigger than 0, log a is less than or equal to a minus 1, where the logarithm is the natural logarithm, with equality if and only if a is equal to 1. Instead of giving a proof, this inequality can be seen to be true with a very simple plot. The x-axis here is a, and it is clear that log a is less than or equal to a minus 1. A corollary of the fundamental inequality is corollary 2.30. It says that for any a bigger than 0, log a is bigger than or equal to 1 minus 1 over a, with equality if and only if a is equal to 1. Here is the proof of the corollary. Let a equals 1 over b in the fundamental inequality log a less than or equal to a minus 1, where b is bigger than 0, so that a, which is equal to 1 over b, is also bigger than 0. Now, by the fundamental inequality, we have log 1 over b is less than or equal to 1 over b minus 1, or minus log b is less than or equal to 1 over b minus 1, or log b is bigger than or equal to 1 minus 1 over b, which is the inequality that we need to prove. Equality holds if and only if 1 over b is equal to a, and a is equal to 1, that is, b is equal to 1. Theorem 2.31 is a very important inequality called the divergence inequality. It says that for any two probability distributions P and Q on a common alphabet script x, dpq is bigger than or equal to 0 with equality if and only if P is equal to Q. Now we prove the divergence inequality. First, for simplicity, assume that SP is equal to SQ. For a proof without this assumption, please see the textbook. Now consider divergence between P and Q is equal to summation x in SP, px log px divided by qx. Now change the log to the natural logarithm, and by doing so, we multiply by the constant log e. Now, by corollary 2.30, log px divided by qx is bigger than or equal to 1 minus qx divided by px. Now this px cancels with this px, so we have log e multiplied by summation x in SP px minus summation x in SP qx. Now with the assumption SP equals SQ, we can replace SP by SQ here. And so we have log E multiplied by the first summation, which is equal to 1, minus the second summation, which is also equal to 1. So we have 1 minus 1, and hence we have 0. This proves the divergence inequality. Now for equality to hold in 2, we see from corollary 2.30 that this is the case if and only if px divided by qx is equal to 1, or px is equal to qx for all x in SP. This proves the theorem. Theorem 2.32, called the log sum inequality, is a very useful inequality that can be proved by the divergence inequality. It says that for positive numbers a1, a2, so on and so forth, and non-negative numbers b1, b2, so on and so forth, such that summation ai is less than infinity, and summation ibi is between 0 and infinity. Then, summation iai log ai divided by bi is bigger than or equal to summation iai log summation iai divided by summation ibi, with the convention that log ai divided by 0 is equal to infinity. Moreover, equality holds if and only if ai divided by bi is equal to a constant for all I. To illustrate the log sum inequality, let us look at the simplest example. a1 log a1 divided by b1 plus a2 log a2 divided by b2 is bigger than or equal to a1 plus a2 log a1 plus a2 divided by b1 plus b2. Now we prove the log sum inequality. First, we let ai prime equals ai divided by summation j aj, and bi prime equals bi divided by summation j bj. That is, we normalize ai into ai prime and bi into bi prime. Then, ai prime and bi prime are probability distributions. Using the divergence inequality, we have 0 less than or equal to summation I ai prime log ai prime divided by bi prime. Now ai prime is equal to ai divided by summation j aj, and bi prime is equal to bi divided by summation j bj. With this, we have summation I ai divided by summation j aj times log ai divided by summation j aj divided by bi divided by summation j bj. Now let us color code ai, bi, summation j aj, and summation j bj. In the next step, we move summation j aj outside summation I because summation aj does not depend on I. And for the rest of the term, we simply move them over. Now in the next step, first, we move over the constant 1 over summation j aj, and for the summation inside the square bracket, we're going to break it up into two summations. The first summation is summation I ai log ai divided by bi. And the second summation is minus summation I ai log summation j aj divided by summation j bj. Now the term log summation j aj divided by summation j bj does not depend on I. So in the next step, we put a parenthesis around summation iai. And upon cancelling out the term summation jij, we obtain the log sum inequality. Equality holds if and only if for all I, ai prime is equal to bi prime, or ai divided by bi is a constant. The theorem is proved. We have seen that the divergence inequality implies the log sum inequality. It can be shown that the log sum inequality also implies the divergence inequality. This is left as an exercise. Thus, the two inequalities are indeed equivalent. The next inequality is called the Pinker's inequality that relates the divergence between two probability distributions P and Q and the variational distance VPQ between the two probability distributions. This inequality says that dPQ is bigger than or equal to 1 divided by 2 log 2 VPQ squared. That is, the divergence between P and Q is lower bounded by 1 over 2 log 2, the square of the variational distance between P and Q. If either the divergence between P and Q or the divergence between Q and P is small, then so is the variational distance between P and Q. For a sequence of probability distributions Qk, as k tends to infinity, if either the divergence between P and Qk or the divergence between Qk and P tends to 0, then the variational distance between P and Qk also tends to 0. In other words, convergence in divergence is a stronger notion than convergence in variational distance. For details, please see problems 23 and 24.